Okay, welcome back. And we're going to continue with some of these Lewis structures. And I had said I would do exceptions to the octet rule, so I'm gonna do that, and then I'm gonna review one of them. Um, let's start with what happens if you have an octet violator, like beryllium or boron. So let's say we were making the Lewis structure for boron trichloride. So I follow the same format as before, count up the valence electrons. And boron is in group 13, so 3-tene, and chlorine is in group 17, so 3 times 7. So that's 24 electrons to try to make my diagram. Now, we said the halogens are very unlikely to ever be central atoms. So we're going to put the boron in the middle, and we're going to connect the 3 chlorines. And that uses up 6 electrons and leaves me 18 for the octets. Now, normally I would think, wait a minute, there's not enough electrons here. I need 6 for each of the chlorines, and I need 2 more on the boron. That's a total of 20. But boron is stable with only 6 electrons. So it is an octet violator, and we can go back and we can just use the 18 electrons to complete the octets on the chlorine, since we do not need an octet on the boron. Second type of octet violator we had said was expanded octets, and that's difficult, so I want to do one more of those. The triiodide ion is something I use a lot in AP for a starch indicator, and what it does is when we run a reaction with it, it turns purple, so it's easy to see. And the triiodide ion, if we were to do that structure, again, we follow the same format. Iodine's group 17, so we do 3 iodines times 7 electrons. But there's a -1 charge, so we're going to add an extra electron for that charge, and that gives me 22 electrons. So I would say, all right, the issue with iodine is that halogens are normally terminal atoms. But we have to connect the 3 together. So we're going to connect them in that order. And yes, one of the iodines is going to have to be a central atom. I said the bigger that the halogen is, the more able it is to accommodate charge. And it's able to form and be a central atom rather than just a terminal atom. In this case, we don't have any choice. So that uses up 4 of the electrons to create that bond. And then you say, all right, well, I need to go ahead then and complete my octets. So 2, 4, 6, 8, 10, 12, 14, 16 to complete the octets. And the rule is, if you have extra electrons, let's expand the octet. Expanded octet. And we're going to take those 2 electrons and we're going to put them on the central atom. So generally the way they draw it is they just kind of try to spread the electron pairs out. So I'm going to put 2 here and 2 here. And then we said with an ion, you put brackets around it and you put the charge around the outside of the ion. So there's our expanded octet, a violation of the octet rule, but iodine can do it because it's got that d orbital spacing. And the last octet violator I wanted to do was what happens when you have a molecule that has an odd number of electrons. Nitrogen dioxide is a component of pollution, comes from automobiles, and it exists as a stable, what's called a monomer, which is one part of a material. It eventually forms a dimer, where you put 2 of those together and you get N2O4, but we don't care about that. That's advanced chemistry. We're just going to deal with this nitrogen dioxide. I'm going to treat it the same way I always do. I'm going to add up the valence electrons. 5 for the nitrogen, plus 2 times 6 on the oxygen, and that gives me 17. Now I have an odd number. These things have to work in pairs. That means that there is going to be a singlet somewhere. Single electron, singlet. And when you have a singlet, you're supposed to have 2 electrons. That actually is a deficiency in charge. So singlets are deficiencies. Deficiency, okay, whatever. All right, so we're going to treat this the same way we would. Now, nitrogen and oxygen could both be central atoms. Here's the rule. If they don't tell you which atom is the central atom, make the electropositive one the central atom. Nitrogen is on the left side of the formula. Usually they put the left one as the electropositive, and the one on the right is the electronegative atom. So we're going to put the electropositive one in the center. And the reason being is that if you have an electropositive element in the center, the ones that are electronegative can spread out their charge. They can do what we talked about in the last chapter with polyatomic ions, is this hyperconjugation. Remember I said the analogy was if you had a bald person, you could give a little bit of their hair to them and cover up the baldness. Doesn't solve the problem, but it helps spread the problem out, and that's what nitrogen dioxide does. So we're going to treat this as the nitrogen being the electropositive central element, and we're going to put the two oxygens in the terminal positions, and that's only going to use 4 of our electrons. So that leaves me with 13 to complete the octets, but I would need a total of 6 more electrons for each oxygen. That's 12, 14, 16 to complete the nitrogen. So I don't have enough electrons to complete all the octets, so I'm going to try a double bond. At this point it doesn't matter which side we put the double bond on. It will later, but for now it doesn't. And that's going to use up, instead of 4 electrons, that's going to use up 6 electrons. And you're saying, well, wait a minute, what do we do with those extra electrons now? Because we're still not satisfying the octets. We're going to do the best we can. Here's 2, 4 to complete oxygen's double bonded, the double bonded oxygen's octet. The single bonded oxygen is going to need 6. And we're only going to put 1 on the nitrogen. Now, that's going to create a deficiency there. We have 7 electrons around the nitrogen, and normally nitrogen needs 8. But we don't have that extra electron. We have a singlet somewhere. And then you got to say, well, okay, we've got to put the singlet somewhere. Why did we put the singlet on the nitrogen? Well, the nitrogen is electropositive. Or at least it's not as electronegative as oxygen. It's more electropositive. And remember I said at the beginning of the year, treat positive charges like they're a deficiency and negative charges like they're a surplus, because all atoms are surrounded by electrons. They all have some sort of negative charge on the outside, some sort of positive on the inside. But we're going to say that the nitrogen just isn't going to have enough, and that actually makes sense. If we have to deal with a singlet, which is the deficiency, we're going to put the deficiency right here on the more electropositive element. So this would be our Lewis structure for nitrogen dioxide, and that's about as hard as that gets. I mean, that is advanced, but you're honors, so we throw it in there. So anyway, so that's my completion of the different types of Lewis structures, and I'm going to tell you what they're used for in the next show.